So we just looked at how using slope fields can get us an approximation of a solution to a differential equation. And now we're going to look at ways that we can actually solve them. But first you got to keep in mind that not all differential equations can be solved analytically, and by that, by like writing out steps. A lot of these have to be done on a computer. But what we're going to look at today is equations that are considered first order and belong to this class called separable equations. So let's look at, just like a refresher on what we're talking about again. We have this differential equation is equal to a function that is respect to two different variables, one being an independent variable, time usually, and then an unknown function. Okay, so we're still talking about that. And we can attempt to solve these, and the book says we have a chance of solving one of these equations if we can get it into the form of this, okay? And what we're looking at here basically is if we can have the y, the function in terms of y on one side and the functions in terms of t on the other side, and everything is being multiplied, okay? And that's a big deal. If we can do that, then, this, I think you can see where the name comes from, separable. Like we separated the function that's in terms of t from the function that's in terms of y. If we can do this, then we do have a chance of solving these. And I do want to stress again that these are all multiplied, okay? Anything that would have functions added would not be in this class of separable. So, this would be kind of a factor, and this is a separate factor. So only if we can write it like this are they separable. So make sure you keep that in mind. If we can manipulate this differential equation into something like this, the procedure is actually quite easy. I guess that's not exactly true. If we can do it, it's actually easy. Now, again, make sure you understand, like, not all differential equations that can be written this way can actually be solved analytically either, okay? So, obviously we're going to be looking at ones that can, but this is not, how every single differential equation can be solved. So this is the, procedure. I just took this picture out of the book, and so it's worth looking at, and then I'll do a couple of example problems, and that should get you in a good place for this first section of problems. This is a 4-day section that we're going to do, so we'll really have a lot of time to look at it. But, again, it is important that it can be written this way. And, we have this dy dt. Okay, and so then they're separated if the function in terms of y is on one side and the function in terms of t is on the other side. And then we actually get the dt over here with the function in terms of t and the y with the y here. And then this makes it so that we can integrate both sides, okay? And then, so, we're just doing a pretty simple integration step to both sides. Well, I don't know if it's simple, but you're just integrating both sides using our integration rules. And then, step 3 says that each time you integrate with an indefinite integral, you get a constant. But we only need to write it once, okay? And it's usually standard to write it over here on the right-hand side. But in reality, you get a plus c here and a plus c here, but you only write it once. And then if you're doing an initial value problem, and they give you an initial condition, then you're supposed to go ahead and solve for c. All right, so I'm going to do a couple examples for you here. And this one is one that does not have an initial condition. So we're just going to separate these. And, it is something that we can separate, or at least at first glance, it looks like something we can separate because we have two factors here, the y factor and another factor that involves only x. So what we're going to do is, I think I'm going to start off by multiplying by this dx part. And we would have dy equals y times x squared plus 1 dx. Okay, and we do need to move the y term over, and we'll do that by dividing. And so then we would have dy over y equals x squared plus 1 dx. Okay, and sure enough, we do have this in separable form. Remember, that is a function in terms of one of the variables, dx in this case, and another one in terms of the other variable, dy in this case also. And these were just multiplying, so we do satisfy that first part of the procedure. And now all we're going to do is integrate both sides. So then we have dy over y and x squared plus 1 dx. And so when we take the integral of the left side, we're going to have the natural log of y. And it would be plus c, but like I said earlier, we're just going to deal with that once, and we'll do it on the right-hand side. And so the antiderivative of 2x squared would be x to the third over 3 plus x, and then there's our plus c. Okay, so we do want to solve for y, and so that means we're going to flip the logarithm around, and that would make this, y equals e raised to this exponent. And I've heard, I was told that often the constant will be brought out, and so I think that's a, oops, sorry. Let me get rid of that. That should be a 3. Sorry about that. I think that's a fine answer, but I think if we use our exponent rules, that some people would say that this is a better answer. Okay, and so, that's what we're going to say here is our answer. And I want to remind you that, we are able to check this. If you remember back to the first section when we were doing like the basic ideas, we can verify this answer. Okay, and so what we can do, and I'm going to do it on this one, I'm not going to, do it all the time. But, right, we can come back up to this very original equation, right? And so we can check this out. So let me go back down here. So right, this is I guess maybe just so that you know, right? We can write this as oops. Okay, so we can check this as well. So we just got to take the derivative of what we just found. Right, because that's the derivative of y. So, right, if we take the derivative of our answer here, we'll leave that part alone. That's our constant. Times the derivative of our exponent, which is x squared plus 1. Times that. And we're saying that equals y, okay, and so I'm going to leave a little bit of room, y times x squared plus 1. Well, our y that we just found is what I just underlined here, so right? Then we can divide both sides by this, right? So we'll divide by this, these will cancel, and sure enough we have x squared plus 1 equals x squared plus 1. So that would be our answer. Okay, so that's the whole thing. I'm going to do one with the initial value problem now, or an initial value problem now. Okay, so this is number 22, and you see that it is an initial value problem, but we're going to treat it the exact same way here at the beginning. I'm going to rewrite y prime of t as dy dt. Again, this looks pretty separable to me, so I'm going to start off by multiplying by dt. And then dividing by y. And it just so happens that we have this same kind of logarithmic setup again, but the point is that we're going to integrate both sides no matter what is over there. Sure enough, this does work. It's in our the form that we need. So then we're going to integrate the left side and integrate the right side. This one again becomes natural log of y. This one becomes t to the fourth plus t, and then this is where we're going to get our c. And now, you're welcome to solve for y, but this statement that we just wrote is true. And so it doesn't really make a lot of sense to, change it into the exponential form right now. That's just going to make it more complicated. As long as we've done our integration step, we're allowed to use this information right now. And so, since it is an initial value problem, we still have to solve for c. So again, instead of changing it to the exponential, I'm just going to plug this stuff in right now. So we're saying that the natural log of 4 equals 0 to the fourth plus 0 plus c. So then c is the natural log of 4. Okay, so now we can come back and we would have the natural log of y equals t to the fourth plus t. Now we're going to say plus the natural log of 4. Now we're going to, we do need to solve for y. It just made sense to find c before we did that on this problem. Sometimes it may not. So now we'll go to the exponential form here. So then y equals e raised to all of this. And since we have that constant, I'm going to change it to the form like I did on the last problem. And this will actually simplify down nice and pretty for us. Because e raised to the natural log of 4 is just 4. Right, and you're welcome to go check that, but right, that's really the whole process. Okay, so for the final example problem here, I'm going to do 28, and this is in a new section. It says solutions in implicit form, and it's telling us to use technology on this. And so you can look at the directions, but they say use graphing software to plot the solution. So we're first just going to solve it just like we have before, and then I'll show you what you can do from there. So again, we're going to, it looks like it's going to be in okay form. So, there's no addition really going on. We just have two factors. They just are in a fraction right now. So now we have dy dx equals this. So we're going to cross multiply here and have 2 minus y dy equals 1 plus x dx. I'm going to integrate both sides. And so when we do that, we're going to get 2y minus y squared over 2, and then x plus x squared over 2 plus c. Okay, so now we do have to find c here since it's an initial value problem, and it's just going to be 1, 1. So then it's 2 times 1 minus 1 squared over 2 equals 1 plus 1 over 2 plus c. So that would be 3 halves equals 3 halves. And then c equals 0. So our solution then, since c is 0, is just going to be 2y minus y squared over 2 equals x plus x squared over 2. Okay, so that's not solved the way we did before, but we're being asked to use graphing software to plot the solution. So let me do that. Let me bring up a picture here. Okay, so this is Desmos. This is the Desmos calculator that I found on the web. I'll put the link into the assignment for you guys to use. I'm not really sure what all this is for. I mean, it's not being used right now. So here's our solution that we found a second ago, and this is the plot of the solution for us. And our initial value was 1, 1 right there. You can see it on the curve. Now in the directions in the book it says if the implicit solution describes more than one curve, be sure to indicate which curve corresponds to the solution of the initial value problem. Okay, so there's going to be some where, like I know one on the homework, you're going to get all these ovals all over the place, or kind of ovals all over the place. And you got to pick which one is the solution. And that has to do with whatever your initial value is. And again, this one was right here, so it was obviously on this curve. So just take a second to look at which one is on the curve. Again, I'll put the link to this into the assignment for you. Hopefully this was okay, and if you got any questions, please ask.